So, a little bit of a flashback to when we talked about z-scores. This is an example of a normal curve. Now, this, in fact, is a histogram. We would call this a unimodal and symmetric histogram, but you can kind of see that there is a symmetric and unimodal curve if we kind of squint a little. And so we call this a normal curve. In other classes, you may also call this a bell curve because it kind of looks like a bell. Now, we learned about these when we talked about standard deviation. We figured out that from a symmetric unimodal histogram, you could see the average by looking at where the maximum was and sort of figuring out what value matches with that maximum. So in this case, it happened to be 66 degrees, that the average temperature in LA was 66 degrees. But we also talked about how you could see the standard deviation from these histograms. So if we went out 1, 2, 3 standard deviations this way, we would get almost all of the data. If we went out 1, 2, 3 standard deviations this way, we would get almost all of the data. And when we did that in a previous section, we got that the mean here was about 66 degrees and the standard deviation was about 7 degrees. But we could say even more than that. So remember from our 68, 95, 99.7 rule, we know that 68% of our data is falling between -1 standard deviation and +1 standard deviation of the mean. So this light purple section in here is 68% of the area. And then if we add on these two pink wings on either side and we go from -2 standard deviations to +2 standard deviations, that gives us 95% of the data. And if we go out -3 to +3 standard deviations, we're going to get 99.7% of the data. So now we're going to practice drawing a normal curve and using this information to calculate some probabilities. So now I have information that adult women have a mean height of 64 inches with a standard deviation of 3 inches. So I'm going to sketch a normal curve with these features. Now I know that it's a normal curve, and normal for me means that it's going to be unimodal, right? One bump in the middle, and it's going to be symmetric. Okay, now instead of starting with 64 or 3, I'm just going to start with that shape. So I've got my axis here, and then I've got something that's unimodal and symmetric. I know that where the maximum is, that's going to be the mean. It sort of cuts my graph into two symmetric pieces. So I'm going to put 64 right in the middle. And then just like with my sample, how I go out 1, 2, 3 standard deviations this way, I go 1, 2, 3 standard deviations this way. I'm going to do the same thing here. So I'm going to say 1, 2, 3 standard deviations in the positive direction and -1, -2, -3 standard deviations in the negative direction. So let's add standard deviations. So we're going to add 3. So 64 plus 3 is 67. 67 plus 3 is 70, and 70 plus 3 is 73. Now we're going to subtract the standard deviation going in the other direction. So we get 61 inches, 58 inches, and 55 inches. This normal curve, combined with what we already know about normal curves, can actually help me answer some questions about probability. So if you said, what is the probability that an adult woman is between 61 and 67 inches tall, right? If that's what I'm trying to find. Remember, the key idea from this section is that for continuous variables, probability is connected to area. And so if I think about where 61 and 67 are, they are at +1 and -1 standard deviation. And I know that 68% of my data, and therefore 68% of my area, is in this region. So I can say that the probability that a woman's height is between 61 and 67 inches tall is 0.68. And we're just using that 68, 95, 99.7 rule for now. Now you're going to figure out what's the probability that an adult woman's height is between 58 inches and 70 inches.